Here's one final trick for calculating a limit without resorting to a graph or plugging in a bunch of numbers. So let's find the limit as x goes to 0 of x times cosine of 1 over x. Now, it's tempting to use the limit laws to calculate this limit, and if you try, here's what happens. X times cosine 1 over x is a product, so you get the limit as x goes to 0 of x times the limit as x goes to 0 of cosine of 1 over x. Okay, so the limit of x as x goes to 0, we know that one, that's 0. And the limit as x goes to 0 of cosine of 1 over x, well, this is actually one we looked at in class, and this limit does not exist. This is the one where if you graph it, it looks sort of like cosine, except as you get closer to 0, as x gets closer to 0, 1 over x gets really big, and so the graph just goes up and down infinitely many times like this. So this limit doesn't exist. And if you go back and look at the limit laws are only true if both limits exist. Since this second right-hand limit doesn't exist, our entire attempt to use the limit laws fails. So this doesn't help us calculate the limit. We're going to have to try something else. And here's what we can do. Remember, we're trying to find the limit as x goes to 0 of x times cosine of 1 over x. And it looks like jumping to calculating the limit right away maybe isn't a good idea, because we don't know enough about this function yet. So let's look at the two pieces that make this function. There's x, and there is cosine of 1 over x. And to figure out what the limit is, we need to have some idea of what each of these pieces do. Well, x definitely never is bigger than its own absolute value. So x is definitely less than or equal to the absolute value of x. But also, x is definitely greater than or equal to the negative of the absolute value of x. Okay, so x is definitely stuck between the negative of absolute value of x and absolute value of x. And what about cosine of 1 over x? Well, cosine never gets bigger than 1. And also, cosine never gets smaller than minus 1. Okay, so putting these together, x times cosine of x, cosine of 1 over x, excuse me. Since x and cosine of 1 over x are trapped to the left of absolute value of x and 1, the product never gets bigger than the absolute value of x times 1. But by the same token, x times the cosine of 1 over x never gets smaller than the negative of absolute value of x. X times cosine of 1 over x is definitely trapped between these two values. Now that we know that, let's go ahead and take the limit. So now we're going to take the limit as x goes to 0. Well, as x goes to 0, what happens to the negative of the absolute value of x? Well, x is going to 0, so the inside of here is going to 0, so the whole thing goes to 0. All right, now on the other side, if x is going to 0, what happens to the positive absolute value of x? Well, by the same token, that is also going to go to 0. But look, now x cosine of 1 over x is trapped in between 0 and 0. So this limit must also be 0. So as x goes to 0, x times cosine 1 over x has to also go to 0. What's really happening here is we were able to trap the function x times cosine of 1 over x in between two other functions. Those two functions go to 0, and so they sort of squeeze our function in the middle. And that's why this fact is called the squeeze theorem. So the squeeze theorem looks like this. If you have a function and it's trapped between two other functions, so say f of x is trapped between g of x and h of x, and the limit as x goes to some x value, say a, of g of x is the same thing as the limit as x goes to a of h of x, and maybe both of those are equal to some number L, then the limit as x goes to a of f of x is also L, because f of x is trapped between g and h. G and h are both going to L, and so f also has to go to L. There's a nice way to sketch a graph of what this is saying. So we have three functions. Maybe g looks like this. H maybe looks like this. And at the x value a, right here, both g and h are going towards the height L. So f, in this case, is trapped somewhere in between g and h. And you can see the graph for f as x goes to a, since f is trapped between g and h, there's just nowhere for f to go as we get closer and closer to the x value a, except to this height L. It's the only possibility. And so that's what the squeeze theorem is really saying. It just says that f is trapped between g and h squeeze f towards the limit L. This is sort of a special case fact for calculating limits, but we'll see it comes in handy every once in a while.